name is Eric Kim from the KGSEA Math Circle, and today we'll be learning how to use calculus to solve physics problems. Before diving in, let's review some basic physics equations that don't involve calculus. Here we have the four kinematics equations, which either help you determine the displacement, velocity, acceleration, or time. The missing variables are each labeled in the corresponding equations. Now, it's important to note that these equations assume that acceleration is constant, meaning it is not changing. Therefore, we often use these sets of equations for projectile motion, since the acceleration of gravity is constant at 9.81 meters per second squared. These equations only work if acceleration is constant, but what if acceleration isn't constant? Then we'll have to use calculus to rewrite some of the equations. By definition, acceleration is the change in velocity over change in time, but writing that using calculus, we can see it is a derivative of velocity with respect to time. Now, if we assume that acceleration is constant, we can derive one of the kinematic equations we've seen before. Using the calculus definition of acceleration, we can solve a differential equation by first rearranging the variables such that the dv and dt terms are on opposite sides of the equation. Then we can integrate, making sure to pay attention to the upper and lower limits. Now, since we assume that acceleration is constant, the integral in the right hand results in a times t. Then we get one of the kinematics equations we've seen before. We can do the same for velocity. Velocity is the change in displacement over change in time, so we can write it using calculus as well. We can also solve the differential equation the same way we've done previously. First, we rearrange the variables and substitute v equals v initial plus at, which is an equation we derived previously. Then solving the differential equation yields change of x equals v initial t plus 1/2 at squared, which is also one of the kinematics equations from before. From this, we can see that the physics equations we've commonly seen are derived from calculus. In fact, you'll see that most physics equations can be derived using calculus. Here's a kinematics problem that requires the use of calculus. I'll give you guys 1 minute to solve this. So the answer was D. To see why D is correct, let's look at the equation we have to use. We have to use the calculus definition of acceleration, which is the derivative of velocity. If we differentiate v equals 2t to the power of 3 minus 2t, we get the following equation for acceleration. Then using t equals 2, which is given in the problem, we can plug it back in the velocity function and get the final answer of 22. Here's another problem that is a little trickier than the problem before. I'll give you guys 1 minute to solve this as well. So the answer was A for this problem. The key to solving this problem was knowing that when net force equals 0, the acceleration is also 0. Then we can differentiate the displacement function twice to get the acceleration function. Then we need to set the equation equal to 0 since we're interested in finding the time when acceleration is 0. Solving the equation, we get t equals 0.5. Now let's look into force, work, and energy. Force is the push or pull of an object that can cause it to change motion. Work is the amount of energy transferred, and energy is the ability to do work. The definition of work and energy might sound confusing, but once you start solving problems, you'll get the hang of it. It's also important to note that work and energy have the same units of joules. Just like before, the equations can be rewritten using calculus. For force, acceleration is dv over dt. Force is also equal to the negative change in potential energy. Work is the integral of force with respect to distance, and the equation for kinetic energy can also be derived using calculus. Note that work is the change in kinetic energy. To better understand why this is true, you can say that the kinetic energy is used to move objects, and as the object moves, it does work. Then we can write work as the integral of force with respect to distance. Recall that F, or force, equals m multiplied by dv over dt. If we assume that mass is constant over time, we also know that dx over dt is equal to velocity, so the equation is integral of velocity, which yields the 1/2 mv squared minus 1/2 mv initial squared. It's important to know how to solve differential equations like this, as we'll look at a similar problem that requires solving a differential equation. Here is a practice problem that requires using the concept of work and energy. I'll give you guys 1 minute to solve this problem. So the answer to this problem is A. The key to solving this problem is knowing that work done is stored as potential energy. Knowing this, we can integrate the force function with respect to distance and get the final answer of 1/2 kx to the power of 4. For the final question, we have a problem from AP Physics C Mechanics, 2008 FRQ number 1. Read over the problem carefully because every piece of information is important for solving the problems which will be shown later. Okay, so before we begin solving the problems, it's always a good idea to draw a free body diagram so we don't get lost later trying to differentiate between force components and actual force vectors. In this scenario, the only forces are the normal force, weight or mg, and the drag force. Also note that the component of weight parallel to the slope is mg sine theta, which will be used later. Now, the problem asks to solve a differential equation to find the velocity function of the skier. Using the free body diagram from before, we know that the force components parallel to the slope is mg sine theta minus bv, where bv is the drag force. We can write ma as m times dv over dt in order to create a differential equation. Now we have a differential equation, and just like before, the first step is to separate the variables. Once that is done, we can use substitution to make the integration easier. Setting u equal to mg sine theta minus bv, we can differentiate u with respect to velocity to get minus b. Now rearranging the equation, we are ready for integration. We know that the integral of 1 over x is ln x, so once we integrate, we get the final equation shown in the bottom right corner. However, we do not know the value of c in this equation. Therefore, we need to use the initial conditions given in the problem, which is v equals 0 at t equals 0. Plugging these values in, we can solve for c and get the final equation boxed in red. To summarize, almost all physics equations can be written and derived using calculus. Examples are the kinematics equations and the work-energy theorem. When integrating, you should pay attention to the upper and lower limits because most physics problems will be based on definite integrals. Finally, when solving differential equations, it is important to first separate the variables. Then when integrating, it might be helpful to use substitution to not get lost in the process. And lastly, check the initial conditions to make sure the unknown variable c is not neglected. Thank you for listening.